Dear friends, with this video I want to offer you an alternative method for solving mechanical problems, for instance the equilibrium of a mechanism. If the mechanism is made of few elements, the use of the cardinal equations can be difficult and very long. This method actually is not new. It was discovered by Giuseppe Lagrangia, better known as Joseph Lagrange, and it can be applied for statics and for dynamics. In this video we will see an application for the statics. Let's start together. As usual, we start with the definition of the problem, then we introduce the experimental phase consisting in a double trial, once with single and once with double spring. The following step is to determine the spring constant, and this result we need in order to solve the problem analytically. The task of the presentation is to approach the Lagrange method. This method we display here, and to confirm if the method is correct, we solve also the same problem using the statics equations. Finally, we discuss how the theoretical results are matching the experimental data and what are the reasons for deviations.
Today I want to introduce you a new experiment that is built here. We have two bars made of steel joined in 1, 2, 3 points. One point is fixed, the second point is moving together with two bars, and the third point is connected to a sledge that can move horizontally thanks to the guide. And on the end of the guide we have a spring. The task of the experiment is to find the equilibrium configuration, or in other words, what is the force required by the spring to lift the bottle. Actually, we start first the experiment and then we try to get the result analytically by using the Lagrangian mechanics. The advantage of Lagrangian mechanics we will see, because it is much simpler than using the equations of the statics, especially because in this case we have only 1 degree of freedom, that is the position of the sledge, or in other words the elongation of the spring. For metering all the parameters we have our tape meter, our caliper and our dynamometer.
The mechanism of the experiment is represented hereby. It consists of 3 rigid bodies, 2 equal steel bars and a sledge, having following constraints. The bar number 1 has a fixed pivot at the left end, capital O, and it's joined with a movable pivot at the right end, capital P. This pivot is in common with the bar number 2. The bar number 2 end has also a movable pivot, capital Q, joined to a sledge to move horizontally along a guide. At the opposite side of the guide there is a spring. The right end of the spring is fixed to the guide. In the middle of the mechanism is applied the vertical load, capital W. We consider the mass of the 3 rigid bodies negligible with respect to the mass of the load. The system has only 1 degree of freedom, that is the angle theta, or the displacement of the sledge delta x. Those are linked together, and because of that we can describe the system configuration using only 1 parameter. Before starting the experiment we need to get all the measurements, also the lengths and the weights of the mechanism. The length of each bar is 270 mm, that is the distance between the pivot OP and PQ. This distance is fixed. The distance of the sledge at no load, that is the length OQ, 370 mm, and this distance changes with the load. Then we determine the angle θ0 at no load with a simple trigonometric relation we find 46.7 degrees. Finally, we measure the weight of the bottle full of water. That is exactly 2 kilograms. The first experiment is to measure the displacement of the sledge delta x, that is the spring elongation after the load is applied. And since we want to be precise, we need a caliper. We measure first the spring length at no load, that turns into 63 mm, and then the displacement when the load is applied. The difference says 45 mm. Also, the displacement delta x of the sledge is 45 mm when the load is applied. In the same way, we run the second experiment, but in this case we are using two parallel springs instead. By repeating the same procedure, we find a displacement of the sledge being 19 mm. Now we need a second set of trials, as anticipated, to get the spring constant, both for the single and for the double spring. The procedure is as follows. We measure the force at each preset elongation step, respectively 50, 100 and 150 mm. Then we find by a linear regression the result, and the slope of the line is the constant to be found. The same we repeat for the double spring. The results are summarized in the table. The data are plotted in the charts, respectively for the single spring, the green line, and the double spring, red line. We built the regression line and we get the equation for each one. The x coefficient represents the spring constant in kilogram force per millimeter. Finally, we convert the value into Newton per millimeter, and we find 0.193 and 0.384 respectively. We observe that the constant for the double spring is twice the constant of the single spring. This result is confirmed by the theory because we are dealing with two equal springs in parallel. We have to come now to the most interesting part of the presentation: how to solve the problem analytically by using the Lagrangian theory. First of all, we resume the assumptions used in the model. The weight of the bars is negligible with respect to the applied weight, the bottle. There is no friction, and there is linear behavior of the springs. The method says we write the potential energy of the system, capital V, sum of the gravity potential and the elastic potential energy. The first one we can express as a product between the mass, the gravity constant, and the vertical displacement y, with minus because in our representation the y-axis grows towards the bottom. The second part, the elastic potential energy, we can express with this formula, where delta x is the elongation of the spring. If we express y and delta x by using the angle theta, we find this expression, where capital V, the potential energy, is only a function of the variable theta. Then we make the first derivative of capital V versus theta, and we put this equal to 0. We solve for theta. We need a numerical approach because the equation is transcendent, not analytically solvable. The result says for theta 52.24 degrees. That is the equilibrium position when applying the load in case of single spring, and gives for the displacement 39.3 mm. If we repeat the same procedure for the double spring, also using k prime in place of k, we get theta prime 49.81, that is a displacement of 21.5 mm. We represent in the table the results and we compare those with the experimental values. In the last row there is the difference. We will comment the result at the very end of the presentation. Let's find the analytical solution by using the classical method, that is, the statics equations. To apply the method, we need first to define all the forces acting to the system. Beside the applied load capital W, we have three more external forces: the reaction at the pivot O, capital R, the reaction at the guide, capital N, and the spring force, capital F. For the time, we don't care of R because it won't appear in the equations we are considering. The first equation we apply for the complete mechanism and says the sum of the moments of the external forces with respect to the pivot capital O must be equal to 0. Here they appear only capital W and capital N, and we find a relation linking capital N with applied load. The second equation we apply only to the system made by the bar number 2 and the sledge. It says the sum of the moments of the external forces with respect to the point capital P must be equal to 0. And here we find a relation between capital F and capital N, where F is negative k times delta x. If we combine the two equations together, we get a relation in the red frame that is formally equal to the one found by means of the Lagrangian method, and that confirms the assumption. Some general observations. The force at equilibrium condition we can calculate multiplying the displacement and the constant of the spring, and that we can do both for the single spring and for the double spring. We get the values of 0.77 and 0.84 kg force respectively. That is significantly less than the load. Therefore, the mechanism is convenient. Which are the main reasons for deviations between analytical and experimental data? Most probably, the friction cannot be neglected, and the spring is not perfectly elastic, as per our assumption. Moreover, there are some uncertainties in the readings. The Lagrangian method is convenient if there are many rigid bodies with few degrees of freedom. In our case, it was only 1 degree of freedom, and when the potential energy is easy to express. We remember that the Lagrangians can be only used if there are conservative forces, otherwise we cannot define a potential energy, and if the constraints are only dependent upon position. As general remark, here we have used only a limited application of the Lagrangian method, valid for the static case. For the statics, only the potential energy is considered. A more complete example will be displayed in the next presentation, while considering the dynamic case, where beside the potential energy, also the kinetic is there. I hope you have enjoyed the presentation. In the next video, we will see an application for the Lagrangian dynamics. See you, bye bye.